Hello, calculus students. So we're getting into something today that is going to be so wonderful. We're going to learn shortcuts or rules for evaluating derivatives so that we no longer have to use the limit definition of derivative every time. And what I want to do in this video, which is optional, is I want to show you the process we could use to derive the formula I'm going to give you in video number 2. I really don't like to just give you a formula out of thin air. It just seems like some magic trick. I would rather have you understand where the formula came from. However, I know that the other video, the required video, is already going to be really long and there's a lot of information, so I figured I would make this part optional. So you don't need to take notes on it, and you might just want to even watch it at double speed or 1.5 speed or something like that. Okay, so for problem number 1, I'm going to find the derivative of f of x equals x. And I'm going to use the definition of derivative that looks like this. F prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. We could use the other definition of derivative, but I just happen to like this one for the series of problems I'm going to do. So f prime of a is going to be the limit as x approaches a of f of x, which is just x, minus f of a. Well, if I put a in there, I'm going to get a over x minus a. Now we can cancel x minus a from the top and the bottom. And we have the limit as x goes to a of 1. Whenever you have the limit of a constant and there's nowhere to plug the a in, you just get that constant. So the answer is 1. So another way I can write this, if I want to use Leibniz notation, is I can say the derivative of x with respect to x is 1. Okay, so we're going to go through a series of several of these and then compare them and draw a conclusion. Number 2, f of x equals x squared. What's the derivative? Okay, so we have the limit as x goes to a of f of x minus f of a over x minus a. I'm going to put our function in there, so it's going to be the limit as x approaches a of x squared minus a squared over x minus a. Now that's going to be 0 over 0, so we're going to factor the numerator. It's a difference of squares, and it factors into x minus a times x plus a. And then we can cancel the x minus a's. And now if we put a in for x, we get a plus a, we get 2a. So that's f prime of a, so f prime of x is 2x. So the derivative of x squared with respect to x is 2x. Okay, number 3. You're going to start to see a pattern. This one is f of x equals x cubed. I want to know the derivative. So f prime of a is the limit as x approaches a of the function x cubed minus the function evaluated at a cubed, over x minus a. Now x cubed minus a cubed is a difference of cubes, and we have a difference of cubes factoring formula that you learned in pre-calculus. It factors into x minus a times x squared plus ax plus a squared. Please note that x cubed minus a cubed is not equal to x minus a quantity cubed, because x minus a quantity cubed is x minus a times x minus a times x minus a. So if you do all that, you're going to have a whole bunch more stuff like this. Okay, that's over x minus a, so we can cancel the x minus a's. And now we can substitute the a in for x, so we get a squared plus a times a, which is another a squared, plus a squared. So that's 3a squared. So that's f prime of a. So that means f prime of x is 3x squared. So the derivative of x cubed with respect to x is 3x squared. Okay, now I'm going to jump a little bit And I'm going to do f of x equals x to the sixth. What's the derivative? So, same idea. F prime of a is the limit as x approaches a of x to the sixth, the function, minus a to the sixth, the function evaluated at a, over x minus a. Well, I never did memorize any kind of factoring formula for x to the sixth minus a to the sixth, or any kind of difference of sixth powers, but every time we've done one of these problems, we have found that it factors into x minus a times something, and that was really helpful because then we could cancel with the x minus a on the bottom. So I suspect that that's going to happen. So here's what I'm going to do. I'm going to use synthetic division. And when we're dividing by x minus a, we would put an a in the box. We have 1x to the sixth, 0x to the fifth, 0x to the fourth, 0x cubed, 0x squared, 0x, and then our constant minus a to the sixth. Bring down the first number. I almost messed up there. Had trouble writing a 1. Okay, multiply it by the number in the box. We get a, write it down and add. Multiply it by the number in the box. We get a squared, write it down and add. Multiply it by the number in the box. We get a cubed, write it down and add. When you're adding the column. Multiply it by the number in the box. We get a to the fourth, write it down and add. Multiply by the number in the box. We get a to the fifth, write it down and add. Multiply by the number in the box. We get a to the sixth, write it down and add. We get 0. That's our remainder. That means it did go in evenly, and this other thing here is the other factor. So that would be 1x to the fifth plus x to the fourth. These are the coefficients that occur on the new polynomial, plus a squared x to the third plus a cubed x squared plus a to the fourth x plus a to the fifth. That's what that all is. So I'll just write that down. I'm going to run out of room, huh? We'll take care of that. Make some room. Now, I would not expect you to do that kind of derivative by hand, but I'm showing you because I want to convince you of what's going on here. Okay, now it's time to substitute the a in for x. A to the fifth. A times a to the fourth is a to the fifth. A squared times a to the third is a to the fifth. A cubed times a squared is a to the fifth. A to the fourth times a is a to the fifth, plus a to the fifth. How many a to the fifths do we have? 1, 2, 3, 4, 5, 6. 6a to the fifth. So that's f prime of a. So that means f prime of x is 6x to the fifth. So the derivative of x to the sixth power with respect to x is 6x to the fifth. Now let's look at what we have. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. The derivative of x to the sixth is 6x to the fifth. Are you noticing what's happening? Are you seeing some patterns? And what if I put a little invisible x to the 0 on that 1? Do you notice that the exponent on x in your derivative is 1 lower than your exponent was in your original function? And do you notice that your old exponent is now multiplied by your derivative? So if I were to expand this, then the derivative of x to the seventh would be 7x to the sixth. Here's how we say it. Bring down the 7 and subtract 1 to get the new power. The derivative of x to the fourth would be 4x cubed. And we're going to generalize that in the other video when you're taking notes. the derivative of x to the nth, okay, you have to bring down the n, and then you have to subtract 1 to get the new power, so that would be x to the n minus 1. So that's your basic power rule for derivatives. And it doesn't only work for integers like 1, 2, 3, 4, 5, and 6. It also works for any real number exponent. So if you had f of x equals x to the pi, the derivative is bring down the pi and subtract 1 to get the new exponent. So the new exponent is pi minus x. Or if you had f of x equals square root x, think of square root x as x to the 1/2 power. Bring down the 1/2 and subtract 1 to get the new power. Now we would probably write that as 1/2 times 1 over square root x, so then we would combine those and get 1 over 2 square root x. Okay, so now we're going to move on to the required video, and you're going to get that rule plus some other rules plus some wonderful graph-related information. Thanks, everybody.